So let's look at hypothesis tests for one proportion, which we will introduce with a joke. And of course, in statistics, we like to take a joke and analyze it to the point where it's no longer funny. So looking at whether this is evidence of sick day abuse in our Dilbert comic, she says 40% of all sick days are Fridays and Mondays, right? So our null hypothesis of no abuse, right, would be that Mondays and Fridays are taken only 2 out of 5 days on average, right? Which would mean that that proportion is 2/5, which is 0.4, right? And our alternative hypothesis is that it's higher. But of course, we can see here that our sample statistic p hat is exactly 0.4, right? 40%. So she's trying to make a shocking statement to her boss here when in fact there's no evidence of anything at all. Looking at the normal distribution that we use for hypothesis tests, it is just like the randomization distribution that we got used to back in the randomization hypothesis test topics, centered at the null parameter. Now, since we're doing only one proportion right now, that null parameter is always a proportion, and we just call it P naught, or the null proportion. It's the value that shows up in your null hypothesis. And because this is the distribution that we're using, the really correct way to check conditions is to calculate n times p naught and n times 1 minus p naught and check that both of those are at least 10. However, there are various reasons why we sometimes settle for instead just checking n times p hat, the sample statistic, instead of the null proportion, that sample proportion, and n times 1 minus p hat. A lot of the reason we sometimes settle for this is that we have to do it this way for two proportions anyway. It gets quite a bit more complicated with two proportions saying exactly what those counts would be if we're relying on the null hypothesis, because the null value is 0. So we switch to just looking at the counts for two proportions anyway, and that's why I think that this approximate way is good enough. There's no harm in calculating the other ones, right? Another reason why sometimes this way is a little bit easier is that it's going to be exactly the counts from your sample. So if you're given your information in terms of counts instead of proportions, then you already have the exact numbers to compare to 10 if you are using this sort of good enough approximate method. So you'll probably see solutions written up using the approximate way, even though the other way is more correct, just because I don't want to tell students that they need to do it the more correct way when in fact it is much slower and a little bit of a distraction from the overall question. So what this means is that we really can use the exact same method that we used for confidence intervals. When we're checking conditions. Now, our estimate of standard error when we're using a normal sampling distribution, our standard error formula, is also very similar to the one that we saw for a confidence interval, but note that this also uses the null proportion instead of the sample proportion. This we will follow. Since we have to calculate it anyway, we may as well calculate it correctly. And again, it's still for the same reasons It's because this picture here shows the actual distribution that we are using when we're doing a hypothesis test. Everything in a hypothesis test, all of the calculations are based on the assumption that the null hypothesis is true, and therefore the distribution we use for everything is centered at the null proportion, not at the sample proportion. So here we will be sure to use the correct formula when we're calculating standard error. But how you check conditions, it's okay with me if you use either the truly correct way for a hypothesis test or the approximate way, which is what we would do for a confidence interval. Now, the formula we're going to use for our z statistic, this is something that you have already seen, this more general statement of sample statistic minus null parameter over SE. If we fill in what those are in the context of one proportion, the sample statistic is always p hat, the null parameter is always p naught, and so our numerator can be written in a much more compact form, and we get to one formula that we can always use for our test statistic when we are working with one proportion, p hat minus p naught divided by the standard error. So let's put all of this to use now in checking some conditions and setting up and answering a hypothesis test in context. Do cash incentives improve learning? So we're looking at a study in which some students who were preparing for the AP statistics exam were offered cash incentives so that they would be given some cash if they scored a 5 on the exam. And we compared that to all of the students who were not offered cash incentives to see what their scores were, to see if the cash incentive was helpful. So our hypotheses are, our null hypothesis is that the cash incentive made no difference at all, and that in fact we still have 15% scoring a 5 or higher on the AP statistics exam, even with cash incentives. Our alternative hypothesis is that this proportion is actually higher than 15%. So our sample statistic, we are told that 17 out of the 70 students who were offered the cash incentive scored a 5 on the AP statistics exam. So 17 out of 70. If I take this to 3 decimal places, I get 0.243. So that is my sample statistic p hat. I need to write it using correct notation, 0.243. Now here's why we like that approximate way of checking conditions. I know that 17 is the number of students who scored the 5, and that the rest of them, which is 53, which I really just did by taking 70 minus 17, that these are all of my counts for those we are counting and those we are not counting. A lot easier to calculate than to take 15% of my n and 85% of my n. Both calculations are pretty straightforward, but this is quicker. We were given counts, so we don't have to do practically any calculations at all in order to check conditions using the approximate method. And I'm going to go ahead and say yes here. Conditions are met. Now for our standard error, we do need to make sure we use p naught instead of p hat. So p naught is that 0.15 from our null hypothesis. And n, we've decided, is our total sample size of 70. So this calculation for standard error looks like a big square root, 0.15 times 1 minus 0.15, which is 0.85, all divided by 70. Remembering that we always take our standard error to at least 4 decimal places, I get 0.0427. And now our z statistic using this formula again. Z is equal to our p hat, which is our sample proportion of 0.243, minus p naught, which is the value from our null hypothesis of 0.15, all divided by 0.0427. So I get a z statistic of 2.178. And I want to think about whether this is a left tail, right tail, or two-tail test before going any further. Looking back up at my hypotheses, in particular the alternative hypothesis, this is a strictly greater than, it's not a less than, it's not a not equal to, and that is how we know that this is a right tail test. So we're interested in a right tail test. I can draw a picture of what this should look like even before I go into StatKey and know the actual values. It's good to get some practice drawing your pictures first. Here's a normal curve. We're just interested in the standard normal distribution here, so I'm just going to mark 0 at the center and my z statistic on the curve. 2 standard deviations away is starting to get off into the tail, but it's not really far into the tail. So I would estimate that z of 2.178 to be right about here, and since I'm only doing a right tail test, I'm going to only shade the right tail. And now to find that p-value, I'm going to go into StatKey. I can tell that it's a fairly small p-value, but not very small. We may get statistical significance out of this. Now remember that in StatKey we're working with theoretical distributions, and in particular a normal distribution. So I'm going to theoretical distributions, normal. I'm going to accept the standard normal distribution that comes up and select right tail and overwrite this 1.96, which is my default value, with my z statistic of 2.178 and hit OK. Now I get my p-value here of 0.015. And I'm ready to go ahead and state a conclusion. So it looks like, since we weren't given an alpha, at least let's go back and read the original question to make sure. We were not given a significance level to use, so I'm going to state an informal conclusion, which is describing strength of evidence. We have, I would say, strong evidence, not quite small enough to get into very strong evidence, but we have strong evidence that the cash incentive makes a difference and increases the chance of getting a 5 on that AP Statistics exam. So we have strong evidence that a cash incentive results in a higher proportion of students earning a score of 5 on the AP Statistics exam, though for this to be a causal association, we really do need to assume that that cash incentive was applied randomly, that it was randomly assigned to people who were taking the exam, and we weren't given a lot of information about how this study was conducted. So we might just add as a little note, this is assuming that the cash incentive was offered to a random sample of people taking the exam so that that treatment group was randomly selected. It's easy to think of lots of ways to do this study poorly. For example, if a group of students who had showed up at a private tutoring center to get help preparing for the exam, if all of those students had been offered the cash incentive, then you're clearly already starting with a group of students who showed up for private tutoring, and all sorts of other ways that this could have some inherent bias in it. So we have to have a little bit of trust in how the study was conducted in order to make this conclusion.